Today we are diving into a fascinating journey through space. No, not outer space, but the spaces we see, remember, and understand every day. Imagine teaching AI not just to look at a room, but to truly understand it. Where the furniture is, how far the fridge is from the sofa, or even how to navigate to the window without bumping into the bed. The paper is all about a benchmark called VSI-Bench, designed to evaluate how AI models process and reason about 3D spaces. We'll explore how models think spatially, their strengths, and where they still need a GPS. Let's jump in.
Have you ever thought about how an AI might learn to navigate and understand a space? Sort of like how we do when we walk into a new room? This research explores how multimodal large language models can see, remember, and recall spaces, almost as if they're forming their own mental maps. Picture watching a video of an apartment or a factory floor. As the video plays, the model identifies objects like chairs, cabinets, or machines, and then arranges them in its own internal representation, a cognitive map, that places these objects in relation to one another. Instead of just listing what it sees, the model builds a spatial structure in its mind. By doing this, these models start to reason about the physical world in a more human-like way. Essentially, they're thinking in space. We will refer to multimodal large language model simply as MLLM from now on. Now, imagine you ask the model, "How far is the keyboard from the TV?" Or, "How many cabinets are in this room?" This study dives into these very questions, testing how well MLLM form cognitive maps from videos and how effectively they recall these layouts. Check out Figure 1 here on the page. It gives you a quick look at how these models turn visual and language inputs into spatial relationships. The abstract sets up the core challenge. We humans are pretty good at remembering spaces just from observation, but can an AI get close to that level? To find out, the authors built a benchmark called VSI-Bench, with over 5,000 question and answer pairs designed to test spatial thinking. The early results? Models do okay, but still trail behind human abilities. Interestingly, simply adding more linguistic reasoning, like chain of thought, doesn't boost spatial skills much. However, getting these models to explicitly generate a cognitive map makes a big difference, especially when the task involves judging distances or recalling where objects are. Think about how you picture your own living room when deciding if a new piece of furniture will fit. With just a quick glance, humans can remember the layout of a room, the sizes of objects, their positions, and how everything fits together. This mental power is called visual-spatial intelligence. While MLLMs are getting pretty good with words, their spatial intelligence is still a growing area. And shucks. And that's important. Spatial reasoning matters for all kinds of applications. Robots navigating a warehouse, augmented reality systems placing virtual objects in your home, or self-driving cars understanding streets. To tackle this, the authors introduced VSI-Bench, a video-based benchmark with 5,000 Q&A pairs spanning nearly 290 real-world spaces. Look at Figure 2 to see how they break down visual spatial intelligence. It includes skills like perceiving objects, reasoning about their positions, handling time-based changes in a scene, and even switching perspectives. This taxonomy helps us understand what the models can and can't do yet, and what's needed to get them closer to real-world reasoning tasks. To dig deeper, the authors use a framework from dual coding theory. This theory separates linguistic, verbal, and visual thinking. Their findings show that the real sticking point for these models is spatial reasoning, not just basic visual perception or dealing with time. The study explores cognitive maps as a solution. While the models do fine with local relationships, like knowing a chair is near a table, they struggle when asked about the bigger picture, the entire layout of a room. Check out how the page talks about two main aspects of spatial reasoning: relational reasoning and perspective shifts. Relational reasoning is about sizing things up and understanding directions and distances, like knowing whether the sofa is closer to the TV than the lamp. Egocentric, allocentric transformation means switching between viewpoints. Imagine going from a first-person perspective to a bird's-eye view. This perspective shift is crucial for tasks like planning routes or navigating from one place to another, and it's something MLLMs are still learning to handle. Now let's look at the tasks that make up VSI-Bench. See Figure 3 here on the page. It shows different types of questions the models face. Some are straightforward. How many chairs are in this room? Others are trickier. Which object is closest to the fridge, or what appeared in the video first? Some tasks involve changing perspectives, figuring out if something is to the left or right from a certain viewpoint, while others involve measuring object or room sizes. These tasks don't just test one skill at a time. They push models to combine perception, memory, and reasoning. This variety makes it feel more like real-world challenges, where you need to remember what you saw, figure out relationships, and maybe even plan a route through a complex environment. VSI-Bench collects over 5,000 Q&A pairs from 288 videos taken from datasets like ScanNet, offering a wide range of indoor environments, homes, offices, factories, and more. Using object-level annotations lets the authors ask precise questions, like, how many cabinets are in the kitchen, or which object is closest to the door. The tasks fall into three main groups: configuration, e.g., counting objects, understanding spatial relationships; measurement estimation, like guessing distances or sizes; and spatiotemporal tasks, like knowing the order things appear or planning a route. The data is carefully formatted, so the models get consistent input. Most questions are generated automatically from metadata, but some, like the route planning tasks, need human input. The result is a benchmark that puts MLLMs through a realistic spatial reasoning test. How did they put this benchmark together? The curation pipeline started with collecting video scans and annotations, then organizing them into a standard format. Human reviewers helped spot errors early on. Next, they generated Q&A pairs, applied filters to remove unclear questions, and fine-tuned everything until the final set was ready. Check out the breakdown. About 48% of tasks test spatial configuration, 40% focus on measurements, and around 12% deal with time-based tasks like appearance order. They tested 15 different models, both proprietary, like Gemini 1.5 and GPT-4o, and open source, like Vela, Lava, all under zero-shot conditions. This gives a good sense of how different models stack up. To ensure the benchmark's accuracy, they used a human-in-the-loop quality review. This meant going back and fixing any ambiguous questions or unclear annotations. They also chose clear evaluation metrics. For simple yes/no or counting questions, exact match works fine. For numerical tasks like estimating room size, they use mean relative accuracy, which gives a more detailed picture than a simple right or wrong approach. All these quality checks help ensure the benchmark truly measures a model's spatial reasoning, and not just its luck or language skills. It sets a high bar for evaluating models on these kinds of tasks. Check out Table 1 on the page. It shows how different models did on VSI-Bench's 8 types of tasks. Things like counting objects, guessing room size, or planning a route. Humans, tested on a small sample, got about 79% accuracy. Top models, like Gemini 1.5 Pro, didn't break 50% for many tasks, and some open-source models struggled even more. Look at the radar chart beside it. It visually compares human performance with the models. Humans are still way ahead, especially on spatial reasoning tasks. The takeaway? Even today's advanced models have a long way to go before they match human spatial intelligence. As we look at the bottom half of this page, we see the analysis shift to performance comparisons. Baseline methods, like random guessing, set a pretty low bar. Humans easily surpass these. In fact, humans got about 79% right on a tiny subset of tasks, while even the best MLLMs couldn't get within 30% of that score. Proprietary models like Gemini 1.5 Pro do better than most open-source models, especially for things like measuring distances or room sizes. But the gap between human and model performance is still wide. Many open-source models, in particular, fall below even the chance baseline for some tasks, highlighting where improvements are needed. Here we see examples of how MLLMs tackle spatial reasoning with actual video data. The text walks through how a model figures out the dishwasher's position relative to other objects, like placing them in a mental grid. Another example involves planning a route. Even though these models can understand what they're seeing in a video, you'll notice from the error breakdown that they often struggle with truly spatial challenges, like exact distances or complex pathfinding. Check out the error graph. It shows the specific areas where models tend to fail. This helps pinpoint what kinds of reasoning are still tough for them. It's like a roadmap for future improvements. This part digs into how models explain their own reasoning process. The authors use techniques like LLM saliency maps to visualize what the model focuses on. By examining 163 model mistakes, they find patterns. Sometimes models do a good job by establishing a global coordinate system in their head, leading to correct answers. But when they fail, it's often because they can't step back and see the entire space. For instance, they might mess up when switching from their own viewpoint, which is egocentric, to a more global perspective, which is allocentric. This kind of error analysis shows that while models are getting better at understanding objects and scenes, they still lack a true human-like sense of space. As we move on, we see a clearer picture of where models go wrong. 4 error types stand out: visual perception, linguistic intelligence, relational reasoning, and egocentric allocentric transformation. Over 70% of mistakes are tied to spatial reasoning. This makes sense. Spatial tasks are the core challenge in VSI-Bench. Check out Figure 9. It shows what happens when you try different linguistic prompting techniques like chain of thought or tree of thought reasoning. Surprisingly, while these help with language reasoning tasks, they often hurt spatial reasoning performance. Table 2 shows a slight improvement for Gemini 1.5 Pro using chain of thought, but it's not enough. It turns out just adding fancy language tricks doesn't solve spatial reasoning problems. Here, the authors bring up the idea of cognitive maps again, focusing on how LLMs form and use these internal representations. Techniques like zero-shot chain of thought, self-consistency, and tree of thought often fail to help with tasks like judging room sizes or distances between objects. But what if the model actually tries to place objects on a mental grid? That's where cognitive maps come in. With cognitive maps, Gemini 1.5 Pro can place objects pretty accurately relative to each other, at least when they're close. But as objects get farther apart, the model's accuracy drops. This suggests that while models can handle local neighborhoods of objects, understanding the whole space in one go is still tough. Look at Figure 10. It shows cognitive maps that the model generated. Notice how the predicted layouts capture some local relationships but lack a unified global view. Figure 11 backs this up, showing a sharp drop in accuracy as the distance between objects increases. This implies the model is good at local reasoning, knowing what's next to what, but not great at piecing everything together into one big picture. This challenge mirrors what the authors have been pointing out. Building a fully coherent global spatial understanding from a sequence of video frames is hard for MLLMs. Humans do it naturally, but models still struggle to combine all that information into a single, consistent mental map. Here, the study shows that adding a cognitive map can improve how models handle relative distances. For example, Gemini 1.5 Pro's relative distance performance jumps by 10% when it uses a cognitive map. If you provide it with a ground truth map, that improvement goes up to 32%. That's a big hint that mental spatial representations help models achieve a better overall understanding. The discussion then shifts to how video benchmarks like VSI-Bench are becoming more common. Traditional tasks focused on static images, but videos force models to understand 3D spaces over time. It's a trickier challenge, but it's also more realistic. After all, we live in a dynamic, three-dimensional world. Wrapping up, this section summarizes what we've learned. The VSI-Bench framework shows us where MLLMs stand today. They're pretty good at perception and basic language tasks, but they hit a wall with spatial reasoning. Linguistic prompts alone don't fix this problem. Cognitive maps help, especially with tasks like estimating distances, but there's still a long way to go. Look at these findings and think, what's next? The authors suggest that future work could involve fine-tuning models specifically for spatial tasks, using self-supervised learning to teach them better spatial representations, or developing special prompts just for spatial reasoning. The goal is to push MLLMs closer to the kind of spatial thinking we naturally rely on every day. As we finish this deep dive, let's have a bit of fun and imagine the future. Maybe one day these models will navigate virtual spaces as smoothly as we move a couch around our living room. Until then, we'll just keep testing them, guiding them, and watching them grow up in their own digital playgrounds.